Dear students, today I am going to discuss Huygens principle about wavefront. So, how to obtain the new wavefront or position of a wavefront based on the Huygens principle. Firstly, consider a point source. Okay, this is the point source S. So, the light goes in the form of waves. According to Huygens, it is in the form of longitudinal waves. Now, let this be the primary wavefront or the initial wavefront at any time t after the source is on. Now, according to Huygens principle, every point on the wavefront is a source of secondary disturbance, and the secondary wavelets emitted from this point, every point on this wavefront, travel in all directions. The position of the new wavefront is obtained by drawing tangential surface to the secondary wavelets or secondary disturbance. So this is the wavefront, so that every point on this is the source of secondary wavelets. So secondary wavelets travel in all directions we take, and the position of the new wavefront at any time later time t is formed by drawing a tangential surface to this wavelets, secondary wavelets. So let A be inner circle what I have shown. Actually it is not circle, it is a spherical surface. Only in the diagram I can say it is like arc. But it is not arc, it is the spherical wavefront. So AB be the initial or primary wavefront. Now these what circles I have shown, actually they are the spherical wavelets. Spherical wavelets which advance from the primary wavefront. After a time t, they travel a distance c into t. Distance travelled is ct. So these secondary wavelets or secondary disturbance will have the radius ct after a time t from the wavefront B, AB. Okay. Now the secondary wavelets are shown by these circles in the figure. Actually, they are the spherical wavefronts, and this surface CD is the tangential surface drawn, drawn to all the secondary wavelets after a time t. So now this is the new wavefront. Okay, so AB is the initial wavefront, whereas CD is the new wavefront. This is in the case of a point source. Suppose a plane wavefront at large distance. Suppose a plane wavefront we have to assume. Suppose this is the primary wavefront, a plane surface at a large distance from a point source or a line source. This is the wavefront, say AB. AB is the wavefront initially. Now the secondary wavelets originated from this points, all the points on this surface. Okay, secondary wavelets, they advance in all directions. The new wavefront is obtained by drawing a tangential surface to all the secondary wavelets. So this is the CD. CD is the new wavefront. Okay, new wavefront obtained. Okay, so AB is the initial wavefront, initial or original wavefront you can call. Okay, new wavefront is obtained by drawing tangential surface to the secondary disturbance or secondary wavelets. So let me repeat the statement. Huygens principle states that every point on the wavefront is a source of secondary wavelets. The secondary wavelets originating from this primary wavefront advance in all directions. The position of the new wavefront at any time is obtained by drawing a tangential surface. Here it is a spherical surface, here it is a plane surface. So the position of the new wavefront is obtained by drawing a tangential surface to the secondary disturbance or secondary wavelets, which are spherical wavefronts shown in both the figures. So these are the spherical wavefronts. Whatever circles are shown in the figures, they represent the spherical wavefront produced or originated from the primary wavefront. So this is about the Huygens principle. Now using Huygens principle, we can derive two laws of ray optics. One law is Snell's law, another one is Snell's law is for refraction, and another law is law of reflection, that is angle of reflection is equal to angle of incidence. So those two laws we are going to prove using the Huygens principle. So firstly, let me prove the Snell's law. Snell's law states that the ratio of sine of the angle of incidence to the sine of the angle of refraction is a constant, and the constant is equal to the ratio of the refractive indices of the two media. That is, whenever light travels from medium 1, angle of incidence is I, okay, angle of incidence is I, to another medium where the angle of refraction is R, then the ratio sin A by sin R equal to N2 by N1, where N1 is the refractive index of the first medium where I is the angle of incidence, and N2 is the refractive index of the second medium where R is the angle of refraction. So this is the Snell's law, which we have to prove using Huygens principle. So firstly, I will take a surface which separates the two media. Okay, so medium 1 here, medium 1, and this is the medium 2, medium 2. So there are two media. This is the interface, that is the surface which separates the two media. Now wavefront, okay, see the light is incident this way, this is the ray of light I take. Okay, now you see this is the plane wavefront. Okay, so the AB, angle of incidence is I, and I will take this point as here A, B. So AB is the incident wavefront. Okay, so I will take this side. AB is the incident plane wavefront. Incident plane wavefront. Okay. And angle of incidence made with respect to normal. This is the normal. The perpendicular line drawn to the surface. This is the interface separating the two media. If I take say PQ. PQ is the surface which is an interface, the surface which separates the two media. Now angle of incidence is I. Okay, now when the ray refracts here, the angle of incidence is I like this. Okay, now when ray or when light enters the another medium, I assume the velocity of light in this medium be V1, and the refractive index in the first medium is N1. Okay, refractive index in the second medium be N2, and velocity of light or speed of light in the second medium be V2. Okay, N1 refractive index of first medium, N2 is the refractive index of second medium, V1 is the velocity of light in the first medium, V2 is the velocity of light in the second medium. So PQ is the interface which separates the two media. Now you see the ray undergoes or light undergoes refraction at the interface. Okay, that is refraction. So this is the angle of refraction R. Okay, after a time tau, the light travels from B to C. Okay, light travels from B to C like this. Okay, C. Light travels through a distance BC. after a time tau. After a time tau, light travel through a distance BC, and that distance BC equal to V1 into tau. So in a time tau, the light travels from a position B to C. This is the plane wavefront. Plane wavefront is advancing in this way. So the wavefront is touched already. Portion A touched the point A here, the interface. So it is traveling inside the denser medium. Assume that this is denser medium, so that light undergoes refraction, so that ray bends towards the normal, where angle of incidence is more and angle of refraction is lesser. So R is less than I in case light travels from rarer to denser. First medium let it be rarer and this medium be denser. Okay. Now the new wavefront we have to get. New wavefront in the denser medium we have to get. So in a time tau, light travels from B to C. Now at the same time duration tau, light travels from A to some other point D in the medium 2. Okay, so that wavefront I will draw here like this. Okay, this is the position of the new wavefront obtained from the point A, originated from the point A. Then I have to draw the wavefront. Okay, so that is the tangential surface. So not only one, like this we get wavefronts. Okay, so wavefronts, the tangential surface joining all the secondary wavelets, I get the new wavefront, refracted wavefront. Refracted wavefront I get. So, but for sake of simplicity, we will show only one spherical disturbance here or spherical wavelet. Remaining all we don't show here in the figure. Now you see angle of refraction is R, and this is anyway 90 degree. This is 90 degree. If this is I, just observe this is 90 minus I. Because the wavefront AB is perpendicular to the incident ray. Wavefront is perpendicular to the incident ray. So this angle is I, remaining angle must be 90 minus I, total angle should be 90 degree. And again this line is the normal. So if this is 90 minus I, then this angle is equal to I. This angle is equal to I. Now if this is R, this angle will be 90 minus R. Again the same idea, if it is a normal line, straight line, okay, that is perpendicular to the surface PQ, if this angle is R, angle of refraction, then the remaining angle out of 90 degree, perpendicular, normal is always perpendicular to the surface, okay. So if this is R, then the remaining angle will be 90 degree minus R, and this is 90, see, look at 90 minus R plus 90 degree plus something equal to 180 degree, equal to 180 degree. So that should be equal to R. That should be equal to R. That means this angle becomes R. This angle becomes R. So this is the angle of incidence I, and this is the angle of refraction R. Then what happens, you see? Okay. Yes. Now you see what happens. This is the plane wavefront, refracted plane wavefront, refracted plane wavefront. So AB is the incident wavefront, incident plane wavefront, plane wavefront. Whereas CD, this point is D here, where the tangent to the spherical wavelet is drawn. That is the CD. This point I will take as D. So CD is the refracted. CD is the refracted plane wavefront. CD is the refracted plane wavefront. Okay, that's all about this diagram explanation. Next, the derivation part. So all the explanation I have given and diagram I have explained. Now what I have to do is, so in a time duration tau, light travels through a distance BC. In the same time duration tau, light travels through a distance AD in the medium 2. In the medium 1, it travels a distance BC. In the medium 2, in a time tau, light distance traveled by the light is AD. Okay, so then you can define now. So BC equal to V1 tau and AD equal to V2 into tau, because the distance traveled is equal to speed of light into time. Speed of light into time. Speed or velocity magnitude is same. So V1 into tau, here V2 into tau. BC equal to V1 tau, AD equal to V2 tau. Fine. Then we have to consider two triangles. Here right angle triangles you can see, and we need sin I and sin R. We have to define the sine function in the triangle ABC and in the triangle CDA. Okay, so firstly in triangle ABC, sin I equal to opposite side by hypotenuse. Opposite side by hypotenuse. That is the sine definition. So sin I, opposite side is BC, hypotenuse is AC. Okay, so it is BC divided by AC. Next in triangle CDA, sin R, I define the function sin R equal to AD opposite side, so AD divided by hypotenuse. For the angle R, this is 90 degree here, so AD is the opposite side and CD is the adjacent side. Hypotenuse is the longest side in any triangle, and hypotenuse is decided by the angle opposite to side opposite to angle 90 degree or side opposite to right angle. So here angle B is 90 degree, so AC is hypotenuse. Here angle ADC is 90 degree, so AC is hypotenuse. So opposite side AD divided by AC. Now we observe here in Snell's law, we have to take the ratio sin I by sin R. So we have to divide this. Therefore, sin I divided by sin R equal to. So this divide BC divided by AC. This is actually sin I. Okay, now divided by is there. Divided by this ratio divided by again sin R. Okay, AD by AC. Now whenever it is divided by, I have studied in lower class, so multiply the reciprocal. So that is BC by AC into reciprocal you have to multiply, that is AC by AD. Now you can observe here AC and this AC length same, equal, cancel numerator and denominator. So then now sin A by sin R we get BC upon AD. Now that is equal to BC upon AD. BC is V1 tau divided by AD is V2 tau. Again the same time duration, tau and tau cancel. Then I get finally V1 by V2. So that means therefore lastly I can write sin I by sin R equal to V1 by V2. Okay. Now we have not reached the last step. Here we see N2 by N1. We have to express this sin I by sin R ratio in terms of refractive indices. But I have achieved here up to velocity. So in the previous classes, that is in ray optics, you have studied the relation between refractive index and speed of light in a medium. So refractive index is defined as, I write here, refractive index N1. Refractive index of any medium N equal to speed of light C. Speed of light C in a vacuum to the speed of light in the given medium. So the ratio of speed of light in vacuum to the speed of light in that medium. So that ratio of the two speeds or velocities also we can see. So ratio of the velocity of light in vacuum to the velocity of light in the medium gives a dimensionless, unitless quantity, a pure number more than 1 we get, because speed of light is the highest, okay, highest value compared to speed of light in any medium. Speed of light is highest in case of vacuum. So numerator is speed of light in vacuum, which is the highest number. So then denominator will be smaller than that. Hence the ratio will be always more than or equal to 1. If it is vacuum, then refractive index is 1. For any other medium, refractive index is more than 1. Air it is slightly more than 1, whereas for the medium like glass we take approximately 1.5, because there are different types of glasses like crown glass, flint glass, etc. But generally we take a refractive index of glass as 1.5, refractive index of water as 4/3, or a decimal value approximately 1.33. The standard values we take. Okay. So refractive index n is equal to speed of light in vacuum to the speed of light in the given medium. So with this we can write V1 by V2 ratio. How? So V equal to, this implies n equal to C by V implies V equal to C by n. V equal to C by n. Okay. So then I can write here. First medium, velocity V1. So velocity is C by n. Okay. So then numerator is C by n1. Okay. Denominator V2. Velocity of light in the second medium in terms of refractive index. So V2 in terms of refractive index, you can write C by n2. Okay. So from this we can write V1 equal to C by n1 and V2 equal to C by n2. Okay. So velocity of light in any medium is inversely proportional to its refractive index. So V1 equal to C by n1, where V2 equal to C by n2. So now you see, cancel C and C, what I get? So n2 in denominator of denominator, so C cancels. Okay, one step if you want you can write like this here. Okay, C by n1 you can write into n2 by C you can write. Then C and C cancels, and finally we get n2 by n1. Okay, n2 by n1. So that's what we need finally. Sin I by sin r equal to n2 by n1. So here I don't have much space. So in the exam or when you write the answers, you write the steps one below the other. I have written the steps horizontally, but you follow the steps one below the other. Okay, after writing BC by AD, then write V1 tau by V2 tau in the next step below this, and V1 by V2 also next step. So like that steps you have to write one below the other. Here I face a lack of space on the board, so that's why I have written like this. So substituted sin A by sin R is V1 by V2 we got from the previous step. Substituting that V1 C by N1 and V2 is C by N2, that is obtained from the ray optics chapter. Ray optics we have discussed in the regular classes, where the refractive index definition was given, and velocity of light in any medium is speed of light or velocity of light in vacuum divided by the refractive index of that medium. So substituting this C and C cancel, N2 by N1 remains. That's what we need actually, Snell's law. Okay. Or we can also write N1 sin I equal to N2 sin R. N1 sin I equal to N2 sin R. So that's all about the Snell's law proof. Snell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of incidence to the sine of the angle of refraction, sine of the sine function. Okay, trigonometric function, sine, cosine, tangent, secant, cosecant, cotangent. So the 6 functions. So sine function, first one. So sine of angle of incidence divided by sine of angle of refraction is a constant. This value is a constant for the given pair of media. So the ratio, the constant is the ratio of the refractive indices in the inverse ratio, because I is the angle of incidence in the first medium, where N1 is the refractive index of the first medium. R is the angle of refraction in the second medium. N2 is the refractive index of the second medium. Okay, first medium N1, second medium N2, speed also V1 in first medium, V2 in the second medium. Okay, then define sin I and sin R in the figure and label the figure carefully. Incident plane wavefront is AB and new wavefront CD obtained by drawing a tangential surface. The spherical portion you have to show here. The refracted plane wavefront is obtained by drawing the tangential surface. Then angle of incidence I, angle of diffraction R. This is some geometrical work. Okay, I is this angle, R is this angle. Define sin I in the triangle ABC. Define sin R in the triangle ADC. Then we need the ratio. Take ratio sin I by sin R. Cancellation of AC and AC. Then BC by AD remains. Substitute BC as V1 tau. Distance travelled by the light in a time tau is BC equal to V1 tau. So this distance is equal to V1 tau. And in the same time light travels distance AD in the denser medium, because in the denser medium light travels slower. Okay, so that's all about the proof. So this is the important derivation for 5 marks. Sometimes 3 marks also they may ask this question. Okay, most of the times they ask in 5 mark section. Then I will go to prove next question, that is law of reflection. Law of reflection is the angle of reflection is equal to angle of incidence. Angle of reflection is equal to angle of incidence. Okay, so that's what we have to prove. Law of reflection. Law of reflection, that is to prove angle of reflection is equal to angle of incidence. So using the Huygens principle. Okay, so firstly consider a plane surface which is a reflecting surface like a mirror. So this is the plane reflecting surface. It is not a line actually. In our board, on a board we can show only line, but it is a mirror. Okay, plane surface. Now a plane wavefront is incident from this side. Okay, plane wavefront. So this is the plane wavefront incident. Okay, so AB is the incident wavefront. Now this incident wavefront, whenever it is incident on surface, reflected. So the angle of incidence is I. Angle of incidence is I. So after reflection, the wavefront is obtained and the reflected ray goes this way. A plane wavefront is incident like this, reflected wavefront goes this way. Okay, so now the angle of reflection you have to decide here. So I take this surface, this line, reflected ray, incident ray this one, reflected ray like this. Okay, so this is the reflected wavefront, reflected rays. Now to get the wavefront, say light takes a time tau to reach a distance BC. So to travel B to C, the time taken equal to say tau. We can take T also. Time taken by the light to travel from B to C is tau. Now the reflected wavefront we get here like this. Okay. So the reflected wavefront we get here. So this is the 90-degree angle. Okay. This is so now in the figure, this is R, angle of reflection. This is I, angle of incidence. So in the triangle ABC, I get this angle equal to I, and in the triangle, okay, here I have to show one wavefront. So in the triangle ADC, I get angle of reflection R. Now to prove here I equal to R. So in a time tau, light travels to a distance BC, so that is V tau. Okay, the same time light travels AD. So BC equal to AD equal to V tau. Okay, so then after that, one angle is 90 degree, another angle is here 90 degree. So angle ABC equal to angle ADC equal to 90 degree. Okay, then AC is common. Then AC is AC. We which is common to both the triangles. Okay, or it's common to both the triangles. Then what happens? The two triangles are